And welcome back. It seems like we only just started exploring the idea of exactly how we can determine the magnetic fields produced by various current distributions. I don't want to abandon that. We will be returning to different ways in which magnetic fields can be produced. But I want to start looking at the intersection of electricity and magnetism in a little more detail. And we're actually going to be looking at a practical application. So I know that sounds surprising, but let's see what happens. The idea that is behind the electric power distribution system in the world is based upon what we're about to discuss here. This idea of magnetically induced voltage, which is better known as electromagnetic induction. To understand the concept, let's imagine that we have an external magnetic field, and as you see on the screen, there are a whole bunch of little X's on the screen to represent a magnetic field that is pointing into the screen. In this magnetic field, we have a long bar made of conducting material. I've made it copper colored. If you want to imagine it as a copper bar, that's great. Being a conductor, we can treat it as having an equal number of free to move positive charges and negative charges. Normally, those positive charges and negative charges are intermixed with each other, but let's see if we can cause them to separate. What you can imagine on the screen is we have the copper bar in the orientation as you see it, and we move it to the right directly across the screen. Now, if you apply the right-hand rule to determine the direction of the magnetic force on a positive charge that is moving to the right in a magnetic field that is pointing into the screen, at the end of it, your thumb should be pointing up. And if we wanted to determine the direction of the force on a negative charge, well, you take that upwards pointing thumb and you flip it for the sake of the negative charge, and now your thumb is pointing down. So as this bar moves to the right in the plane of the screen, while there is a magnetic field pointing directly into the screen, the different charges that pre-exist inside the conducting material will start to separate from each other. The positive charges will be pushed up along the bar, and the negative charge will be pushed down along the bar. So what is this going to do? It's going to create a voltage. We have a region in which there is excess positive charge, and near it we have a region in which there is excess negative charge. And that's basically how you get a voltage difference, a potential difference. If the positive charges are pushed to the top and the negative charges are pushed to the bottom, the length over which we have voltage is the length of the bar, and we'll call that capital L. Now I want you to think about it. We looked at the situation of a conducting material moving to the right in a magnetic field pointing into the screen. What would happen if we had this conducting bar, and now I've drawn it kind of silver colored, if it's moving to the right, but now the magnetic field is directed to the right? Where would we find the location of the highest voltage? The top, the bottom, the left side, the right side, or perhaps I'm trying to trick you, and the answer is none of it. The charges are pushed apart from each other by the magnetic force. But keep in mind that from an electrical point of view, the positive charges and the negative charges attract each other. So the magnetic force is trying to push the charges apart, whereas the electric force is trying to pull them together. At a particular speed, there will be an equilibrium in which the electrical force and the magnetic force are exactly equal to each other. The electrical force for a single charge goes as Q times E. The magnetic force for a single charge goes as QVB, where we assume theta is 90 degrees. Well, little v, the speed, little v, times b, the magnetic field strength, is then equal to the electric field strength. And if we assume it's a uniform electric field within that conducting material, then we can say that the electric field is equal to the difference in voltage divided by the length over which there is a distance in voltage. So I can say the speed times the magnetic field strength equals the potential difference divided by the length of the bar. We can get a buildup of voltage simply by moving conducting material in a magnetic field. And this happens with airplanes. This is a genuine situation that airplanes have to worry about, because airplane wings are made of a lightweight conducting material, oftentimes aluminum. Because it's made of conducting material, what we have on the wings of the plane, we have a long conducting bar moving in a magnetic field. And so charges will build up on one side of the plane, positive charges on one side, and negative charges on the other side of the plane. And now there's a potential difference, and you have to be really careful when there's jet fuel flying around. Take a look at this question right here. We're going to use the Airbus A380, which has a wingspan of 80 meters. Call that like 250 feet. That's most of a football field. And let's say it has a cruising speed of 275 meters per second. And let's say it's traveling in the Earth's magnetic field, where the strength is 5 times 10 to the negative 5 Tesla. And the question is, what's the maximum voltage that can develop? Well, the maximum voltage that develops depends upon the orientation of the plane with respect to the magnetic field. But if we assume theta is 90 degrees, we'll get that the potential difference has a maximum of the speed times the field strength times the length over which we have separated these charges. And the speed, little d, is 275. The field strength in standard units is 0.00005. And the length over which the charges are separated is 80 meters. And we get 1.1 volts. And that's not much, but when you're dealing with jet fuel, that's an issue. And furthermore, the buildup of charge doesn't necessarily, and this is for complicated reasons, the buildup of charge doesn't necessarily entirely separate once the plane comes to a halt. Sometimes some spots will build up charge, and then that charge will remain there even while the plane is stationary. And so you got to be really careful about that, which is why when you start operating on planes' wings and stuff, typically you're grounded. Now let's think about this. I'm moving a conductor in a magnetic field, and I'm getting an electrical effect. Now, if I could somehow hook up this metallic bar to wires to get a closed circuit, all of a sudden I'm going to have a current running through my circuit. So that gives me an idea. How about we place this conducting bar on conducting rails? The conducting copper bar is free to move, and as the charges separate, the charges themselves can then get onto the conducting rails, and we have a closed circuit, and we'll have a current. So all we need is something that pulls this bar down the length of the rails, and we need that copper bar to remain in electrical contact with the rails for the current to move through the circuit. But while that bar is moving, the force on the charges is non-zero. We start getting a current in the circuit. Once that bar stops moving, though, we no longer have a current in the circuit because the force on the charges, the magnetic force on the charges, is zero. This idea of generating a current in a magnetic field simply by moving a conductor is the basis behind electric generators. What you see are a couple of pictures of electric generators. Notice that they have some circular aspects to them. And that's going to be an important thing as we further explore this topic. But the generators are operating on the basis that moving a conductor in a magnetic field can create a voltage, and if everything is hooked up correctly, it can create a current. To understand how these circular generators work, though, we need to introduce and understand the concept of magnetic flux. We saw electric flux earlier in the semester, and we visualized electric flux as the number of electric field lines that were penetrating through an area. Well, magnetic flux is the same idea, the number of magnetic field lines penetrating through an area. Just as the electric flux is E times A times cosine theta, the magnetic flux is B times A times cosine theta. And otherwise, the behaviors of those two properties are pretty much the same. Now, to make sure you have an understanding of the idea of magnetic flux, take a look at this question right here. We have a long straight wire that's carrying a constant current I, and next to it we place a sphere of radius capital R. Now, let's say the wire does not penetrate the sphere. The wire and the sphere are separate from each other. The wire creates a magnetic field. What's the total magnetic flux passing through the surface of the sphere? Is it mu naught times I? Is it mu naught I over 4 pi capital R squared? Is it 4 pi capital R squared times mu naught I? Is it 0, or do we need additional information? Let's examine the conductor on rails idea, but in the context of magnetic flux. As we pull this bar to the right, consider the number of x's that exist within the region of the closed circuit. The bar is the right-hand side of the closed circuit, the resistor is the left-hand side of the closed circuit, and the two rails serve as the top and bottom sides of the closed circuit. And as the bar moves to the right, the area encompassed by the closed circuit increases, and the number of magnetic field lines increases, meaning that the magnetic flux is increasing. And more generally, we can say that the magnetic flux is changing as the bar moves to the right. Now, can we justify the generation of a voltage by examining it in the context of magnetic flux? And the answer, as it turns out, is yes. We've already said that the voltage difference is equal to the speed times the field strength times L. Well, the speed is equal to the change in displacement over time. So rewriting things, I can say that the induced voltage is equal to capital B times the length of the bar times delta X, which is how far the bar has traveled down the length of the rails, divided by delta T. Now, L times delta X is the change in area. The length of the bar is certainly not changing. The separation between the rails is not changing, but the horizontal value, X, is certainly changing. So the area is changing based on that. And I can say that the induced voltage is equal to B times the change in A divided by the time. And because B is a constant in this problem, it's okay for me to bring it inside the delta. I can say that the potential difference is equal to the change in the quantity B times A divided by delta T. And we're basically saying that B times A is the magnetic flux. So I'm basically saying that the potential difference equals the change in the magnetic flux over time. So perhaps there's something to this idea of changing magnetic flux. If the magnetic flux changes, we create a current. Now, I took a lot of logical leaps there. I ignored a lot of subtleties. But somebody who did not ignore all those subtleties was a British scientist by the name of Michael Faraday. And Michael Faraday used this idea and ultimately proved something called Faraday's law. Faraday's law says that the induced voltage, which is represented by the script E, the induced voltage is equal to minus N, where N is the number of loops, times the change in magnetic flux over time. So he took that result on the previous slide. He said, hey, let's do it for N loops. And then there's a minus sign there that is basically there because of conservation of energy. We'll be discussing Lenz's law in the ensuing lecture. Keep that in the back of your mind, but for now just kind of smile and nod and say, okay, there's a minus sign there. Take a look at this conceptual question. We have on the left, on the lower left, we have a loop that is carrying a current, and you can see the direction of the current. And above it is another loop. And this loop above it is not carrying any current at all. On the right-hand side, we have the same loop in the lower right carrying the current, but now the loop above it is doubled up. So I said, let's assume that the current isn't changing. But what if it is? If the current is changing, then the magnetic field created by that current is changing. And the loop above is going to be in the vicinity of a magnetic field that is changing. Hence, its magnetic flux is going to be changing. And therefore, there's an induced voltage. And the question is, how does the induced voltage differ if we have two loops in the upper set of wire, in the upper wire, as opposed to having just one loop? If we assume in the left situation that the voltage induced in the upper loop is E, or E naught, what can we say about the voltage induced in the upper loop on the right-hand side? Would it be 2 E naught? Is it still E naught? Is it E naught over 2, E naught over 4? Is it 0? Or is it none of the above? The idea of the voltage being created simply by changing the magnetic flux is the issue behind those electric generators we saw a few slides ago. In an electric generator, in order to change the flux, we are not changing the field strength B. We're not changing the area of the loop A, but we are changing the orientation between B and A. And if we change the orientation theta between B and A, we're changing the flux. And if we're changing the flux, we're going to create a voltage. And that is the physics behind an electric generator. If we examine that a little more closely, we imagine a rectangular loop in a magnetic field. Now, this rectangular loop is intended to be a three-dimensional construct. You can imagine the external magnetic field pointing uniformly up, and you can imagine the loop perhaps being shaped like a pizza spatula, one of those big rectangular pizza spatulas with a handle. And you can imagine that being perpendicular or in the third dimension, if you will. And what we do is we rotate it around. Imagine putting that pizza spatula in the oven and somehow twisting the handle around so that the blades, if you will, of that spatula start rotating around. And that's more or less what's happening. Except obviously it's not in a pizza oven. The angle theta between the area vector of the loop and the direction of the magnetic field is changing at a constant rate, and we're going to use omega times time to represent the change in that angle, the angular displacement. We can do the math. although it would take some calculus to do it without too much trouble. So I'm just going to present the result. It turns out that the voltage induced in the coil goes as minus the Women's National Basketball Association times the sine of omega t. Minus omega NBA sine omega t gives us the sinusoidal behavior that you see on the screen, and it's oscillating between the positive maximum omega NBA and the negative maximum minus omega NBA. And the voltage, the fact that the voltage is oscillating up and down, means that the current, which is equal to voltage divided by resistance, is also oscillating up and down. And rather than up and down, we might say it's oscillating between positive and negative. And rather than oscillating, we might say it's alternating. We might call this alternating current. In fact, this is how electric power is more or less generated. We find something that twists these loops around, and it creates this alternating current. We see some examples of coal-fired and nuclear power plants that heat up water into steam. The steam is forced through turbines. The turbines turn the loops in the external magnetic field, and current is created in those loops. And we can extract that current and then send it off to your home. We also see hydroelectric dams. So, for instance, at the Hoover Dam, the dam water passes through the dam turbines that turns the dam loops and creates the dam electric energy. And yes, that was childish. Sue me. Or geothermal, or more and more, wind. The idea is the same. You find some external source of mechanical power. It turns the turbines turn the loops, and current is created in those loops, and you extract that current, and you can basically create the electricity that you get out of the outlets. Speaking of the electricity that you get out of the outlets, they are standardized. It's not like that the electricity generated in the Shenandoah Valley is different from the electricity generated at Virginia Beach or the electricity generated in Denver, Colorado, or Amarillo, Texas. In this country, we have standardized the electric power generation system. The coils that rotate in the magnetic field, it's not just a single loop, there's a coil that is rotating in the magnetic field, do so with a frequency of 60 hertz. And they create a voltage that the so-called root mean square voltage is 120 volts. You've probably heard electrical outlets referred to as 120 volts. The thing is, they don't produce a constant 120 volts. The actual voltage coming out of an electrical outlet oscillates between negative 169.7 volts and positive 169.7 volts. We'll explore later what this idea of root mean square means and why it's used to represent the voltage of an outlet as opposed to 169.7. But let's take a look at this problem. We have standardized electricity. The current oscillates with a frequency of 60 hertz. The so-called root mean square voltage is 120 volts. What we want to do is we want to take 30 meters of copper wire to create a coil. This coil will rotate in an external uniform magnetic field of 0.1 Tesla. And the question is, how many turns will our coil have, assuming it's circular, and what will the area of this coil be? So we know that the maximum voltage, at least you can just trust me on this for the time being, the maximum voltage is 169.7 volts. We want a total number of windings. Let's call that total number N. We don't know what it is yet. We do know that they'll be wrapped in a circle with radius r, so the area of the coil goes as pi r squared. Now, I know the total length of wire. So if I have n loops, then n times the circumference of a loop must equal the total length of wire. So the total length of wire, L, is equal to 2 pi r times n, because 2 pi r is the expression for the circumference. So that already gives us a little bit of information about the radius. The radius has to be equal to the total length of wire with which we start, divided by 2 pi n. And subsequently, the area, which goes as pi r squared, would wind up being equal to L squared over 4 pi n squared. So we've already kind of eliminated one of the variables. The maximum voltage is going to be equal to omega times NBA. Omega, of course, is 2 pi times the frequency, and the frequency we know, it's 60 hertz. So I'm going to replace omega with 2 pi f, n is n, and b is b, but now this area A is L squared over 4 pi n squared. I can simplify it a little bit, and I set it equal to E max. And now we can solve for capital N, the number of loops, which is the only unknown left. Because we know F, we know B, we know the total length of a wire L, and we know the maximum voltage. And what we get is N is equal to about 15.9, so we're going to call that 16 loops. Our coil will have 16 loops as it rotates in this 0.1 Tesla magnetic field. And since the question also asked for the area of the coil, I can find the radius. The radius is equal to 0.298 meters, and that means that the area, pi r squared, winds up being equal to 0.280 square meters. Okay, that's it for now. I hope it's been fun.